G'day guys. Just looking at is there a fat switch? Do certain people, have a tendency to put on weight much easier than others? I mean, obviously, when it comes to people being able to put on weight or not put on weight, has a lot to do with the Randall cycle. So somebody that's eating a low fat or a low carb type diet will have a tendency to lose weight if they basically also lower their intake of calories. But if they eat something which is a mixed macro diet in excess calories, they will blockade at the cell level the ability to take up that energy, starving the cell, and as a consequence, engaging what we call the Randall cycle and forcing a lot of that excess energy in the bloodstream into storage, fat storage. But we do notice differences between people. Some people, can eat a bit more, whether you're going low fat or low carb. So people that are going low fat can consume a bit more fat, even though doing primarily carbohydrates, and still lose weight where others don't. And then there's the other side of things where people that basically are doing a low carb diet, and some can lose more weight than others, even though they're eating exactly the same stuff. And so there are genetic differences. And today we're going to look at the fat switch and some of the implications and how to adjust one's dietary approach to basically, work around those. And people that have done genetic tests, they can actually validate to see whether they have these genes or not. Now, let me just share my screen. Okay, this article goes back to 2015. I remember reading this ages ago, but I forgot all about it. It's called the genetic switch, makes fat cells burn energy rather than store it. So these researchers are looking at the sort of obesogenic type gene switches and how to manipulate those. So as they sort of cover here, a master gene that orders fat cells to burn energy rather than store it has been found. Tinkering with it made mice lose weight as their fat storing cells were converted into fat burning cells, raising the prospect of gene therapy to treat obesity. Yes, the normal sort of things that Harvard University Medical School would get into. Their focus is on let's leave people eating garbage and let's somehow manipulate their genes to basically, burn off that sort of stuff. Who knows what sort of side effects long term? Remember, these things short term on rats, not long term on humans. So the implications are that we're fiddling around with pathways maybe we shouldn't fiddle around with. But this article does give us some other insights, which I'm going to get into shortly. They basically state not all fat is created equal. Humans carry several different types. White fat is the insulating stuff that builds up around the middles, storing energy rather than burning it. So what we call white adipose tissue. And the brown fat that is found in small pockets around our necks. The spinal cord does the opposite, burning calories to produce heat, and which we call brown adipose tissue. Beige fat is somewhere in between. It has a different origin to classical brown fat and is dispersed within white fat cells, but it also burns calories without us expending any effort. Now, they go in this part. In the past few years, we've realised that it may be possible to turn people's white fat cells into beige fat, but it's not easy and involves doing things like exposing yourself to cold temperature or doing strenuous exercise. So we know some of these biohacks that some of the biohackers out there do. You know, go into a sauna and drop yourself into a cold water, all these sort of things that do tend to increase slightly the beiging effect of white adipose tissue. But generally speaking, it's a very minor effect for most people. Strenuous exercise also has a tendency to beige slightly. But again, if you're eating shitloads of crap, it's not going to have profound effects. At the end of the day, building up more muscle mass will have a bigger effect because it increases your metabolic rate. The more lean muscle mass you've got, the greater the metabolic rate. So protein is king there as far as I'm concerned. But getting back to our focus is storer or burner. So this is the genetic side of the coin. So this is the interesting part that we want to focus on. So the genetics, the genetic switch is called FTO, discovered in 2007, very recently, 13 years ago. It is one of the only genes to be definitively linked to obesity. Most studies have got very good associations when it comes to these genes. So when you're looking at people with diabetes, looking at people with obesity levels, these genes are the ones that they have the alleles that we're going to talk about shortly. Okay, let's continue. Some 44% of Europeans carry a variant that raises their risk of obesity by around 30%, increasing body weight by about 3 kilograms. Previous studies have shown FTO works in the brain. That was the early studies. And so may influence appetite and hunger. And that was all the sort of the vagus nerve, the ghrelin system, and all this sort of stuff. They believed that it was very much involved with that, but in recent times. But the latest work suggests it exerts a more potent effect in fat cells themselves. And that's what we've really found. So these genes are directly have a transcriptive effect directly on the adipose tissue, far more prominent. And I would say it's probably secondary, some of these other sort of neurological type effects of the way they affect our appetite and things like that. Anyway, to dig deeper into how FTO works, a team led by Kellis and Melina Klausnitzer of Harvard Medical School looked at the genetic profiles of fat cells from 100 people, 52 of whom had the risk-raising gene variant. In cells taken from people with the risk variant, the team found that the FTO activates two other genes called IRX3. There's one major gene there, and the IRX5, 3 for that. These three also are involved in some other diseases and stuff like that, which direct the cell to store energy in the cell from people with the normal variant. The same two genes are switched off, and this causes the cell to burn energy. So if you've got these variants and, pretty much if you've got the good gene, so to speak, you're basically, these genes, if they're activated and they're switched on, they will actually burn away energy like there's no tomorrow. So, and you can see that in some people where they eat excessive amounts of stuff, and while they may actually increase their fatty liver and stuff like that, but they don't really put massive amounts of, you know, adipose tissue, white adipose tissue, subcutaneous fat, or anything like that. So there's that sort of thing. So we're talking about, the way I view it is that it's, where some people can very easily lose weight, and other people it's really stubborn. They really have to go very, very low in either sugar or fat. And you can see that around the place. There are some people that are basically can still be losing weight. They're doing low carb, and they're basically up to over 50 grams, 60, 70 grams, even up to below 100, up to 80 grams, and still can lose weight. And others that are somewhere in the middle, need to be around the 50 or below. And then others have to be even lower than that. That means 25 and below, or next to zero, before they see any movement in weight loss. And so there are differences in that regard. And so, your mate may be able to basically tolerate a bit more carbohydrate, where others cannot, So there's all these sort of differences and all that. And there are some genetics because of that are implicated in this sort of stuff. Anyway, powerful cells. Kelly's team was able to use gene editing techniques to adjust the function of the FTO gene in fat cells, converting fat storing cells into fat burning cells, effectively turning white fat beige and vice versa. The IRX genes were twice as active in the white fat cells from people that carry the risk variant as they were in cells from people with a variant, meaning that the cells were super storers of energy. So as you can see, that this other gene plays a bit of a role as well. So there are practically no differences, just 1% between brain cells in the different groups. So when it comes to expression, suggesting the impact of FTO on fat cells far outweighs that in the brain. So, which is it's the point that I made earlier when I was talking about the differences that they've actually come about. So basically in the brain, the expression of this gene is minor difference between all these different people, whatever variant you've got. Makes sense. I mean, it has a secondary effect in, appetite and stuff like that and whatever. The big role here is energy storage or not. And I'll get into that shortly. This suggests that for some people, the activity of their fat cells might play a greater role in dictating weight than exercise or diet. Well, I think that basically this ignores the Randall cycle. So while exercise can reduce calories, can burn off calories, at the end of the day, it's the diet that's going to influence the actual, whether you're in a catabolic state or an anabolic state, and the way you actually modify that diet as well, whether you're in the Randall cycle, whether you're engaging the Randall cycle or not. So that's a critical part. These guys are still in the calories in, calories out. That's why they make those stupid statements. But it doesn't negate the reality that we do notice these differences in basically adiposity and also in the way people on doing the exact same diet can actually be losing faster weight than others. So there are some genetic differences. We can't ignore that either. And there are reasons for it. There is a dogma that it all depends on appetite and exercise. They're right on that. It is this sort of dogma um, that it's your choice and everything is decided by your brain, says Kellis. Anyway, we're showing that that your fat cells have a very strong role in all this, independent of the brain, and that's a really important thing. You know, it's something that I've always believed that adipose tissue plays a big signaling role, and I've discussed this in the past by stating how chylomicrons and even the ApoE sort of things, how chylomicrons do as fat comes in, they go into the adipose tissue, and there are signals, on what's coming in and stuff like that and affecting, and they will interact, and they will store some stuff there as well, and the rate of storage will differ. Obviously, if hormone sensitive lipase is activated, then that can mitigate these sort of things, obviously, when you're in a more low carbohydrate state and stuff like that. But at the same time, when somebody that may activate in a big way hormone sensitive lipase and actually have very low or no storage, that means the signaling coming from the adipose tissue is do not bring the stuff here, and the behavior of lipids moving through the system and being the way they're actually being transported and the way they're actually interacting with adipose tissue plays a big role depending on these genes. So this sort of explains why, as I said earlier, certain people can get away with a certain threshold of carbohydrates and others can't. So it sort of explains that difference, these sort of genes. Anyway, now this is their study. But let me just go into this for a sec. The gene therapy for obesity. What's more, when Kelly and his colleagues deactivated IRX3 gene in mice fed a high-fat diet, we know what a high-fat diet is. Basically, high sugar, high fat, Randall cycle. The animals resisted piling on the pounds. Mice with the IRX3 gene active gained an extra 15% of their body weight. I'm thinking that once the IRX3 and IRX5 genes are inactivated, the fat cells are able to burn fat all the time, irrespective of how much the mice eat, exercise, or still awake. So it must be causing a certain level of uncoupling of mitochondria. So this gene must have a direct effect on the mitochondria in that regard, in terms of that switching effect. So you can even still have a obesogenic diet. Obviously, you're not going to be losing weight if you're eating excess stuff, but you're still basically any excess. Your cells are going to be starving, nutrient deficient in a sense, because you're engaging the Randall cycle. And this is the problem with this thinking, because you're still engaging the Randall cycle. Okay, you're just thermogenically, you're uncoupling the mitochondria by activating these genes and basically just burning off, beiging your adipose tissue and burning this stuff off. But the reality is, you're still potentially causing you long-term health problems. You're not resolving the health problems. But again, the reductionist thinking is, oh, let's just turn the switch off. And with some modern futuristic medicine, and who cares about the side effects? And there will be plenty. We don't know what they're going to be, because side effects usually come over long periods of time, not short periods of time. So to be seen. I would love to see a study, a long-term study, doing this sort of stuff, this sort of gene, and see what the consequences are in terms of tissue effects and different tissue effects in these rats, something that hasn't been done. But I would not be surprised to find that there are going to be problematic effects on, in terms of muscle and in terms of bone density and stuff like that. Just because you're wasting away energy in order not to store it, you still basically got the problem that you've got a blockade of the cell, because you're engaging the Randle cycle, and you're still basically starving a lot of tissue from energy. So, I'd be interested to know exactly. So, but that's for another day, sort of things. Kellis, he's a Greek bloke anyway, works at Harvard. Team now plans to see whether tinkering with the IRX genes, but he's still a reductionist dickhead, can make obese mice lose weight. So he's going to be, he says that there are also exploring avenues for possible treatments, including gene therapies that alter fat cells so that they can burn instead of store energy. That means turning them into brown, mitochondrial dense, uncoupled mitochondrial, sort of stuff that I always get concerned when people want to do that sort of level of manipulation. Always get concerned. There are good genetic reasons why these things exist, as mechanisms to basically provide us for a rainy day. Rather than actually looking at changing the obesogenic environment, we're looking at basically changing humans to adapt it to this obesogenic environment. Wonderful. What's new? Alternatively, it may be possible to develop a pill that switches off or turns down the activity of the IRX genes. Probably the safest thing would be to, even though I don't really support these sort of approaches, dietary approaches like a ketogenic and low carb diet are much better, carnivore diet, but the majority of people out there, I would not be into the switching off. I'd be maybe down, turning down the activity, maybe a better option, but it's not a perfect option. Long-term side effects, we don't know. Anyway, what this work shows very elegantly is that a key risk of FTO variants act by limiting the development of beige fat cells. There's a good reason for that. Humans need to store for a rainy day. That's the reason for it. Says, anyway, Mert McKinstein of the University of Oxford, as these burn energy rather than storing it as white fat cells do. A reduction in beige fat cells is predicted to reduce energy expenditure and predispose to obesity, she says. But, as far as I'm concerned, that's how the body's supposed to work. Engage the Randle cycle, you get fat. You disengage the Randle cycle, and you lose fat. That is the way our body has been designed to work for thousands and thousands of years. These people want to start tinkering around, there's going to be side effects and problems, because if you're still engaging the Randle cycle and you're basically wasting away multiple ways and creating a lot of free fatty, a lot of, free fatty acids at a time when there's a lot of energy in the system as well, or thermogenically burning it. Now, that raises temperature of organs and other things. Could that have other deleterious effects in sort of oxidizing stuff that's in the bloodstream or circulating around? Or I'm not saying that it's going to, but who knows what side effects could actually come from all this sort of stuff. It's a concern because basically you're increasing the uncoupling effect, you're increasing that thermogenic effect beyond a certain limit. When we're actually looking at, when you fast, you decrease the amount of magnesium. So what happens is a certain level of uncoupling happens at the mitochondria. So it increases temperature, heat, and all that. It's a protective mechanism and stuff like that. But excess amount in the presence of a lot of nutrients, could there be side effects in regards to that? Potentially. So I'm not really supportive of this sort of, this sort of genetic hacking. It's not biohacking. This is direct genetic hacking against, mechanisms that have been around for, millions of years. So I consider it, dangerous attitudes. Whether these findings will lead to new therapies for obesity is less certain. Merkenstein says, because it's likely the switch between beige and white cells is set during development of the embryo, and therefore it may already be too late to intervene in adulthood. So she's basically saying, well, it's at an embryonic level, so it's probably going to be, not really an issue there, or possibly a hack. Kellis, however, thinks that now the genetic circuitry for FTO and the IRX gene is established, drugs or treatments can be devised to interfere with it to combat obesity, a bit like statins. So, and who knows, there may be parents in the future that want to genetically design their children to have these things switched off or certain things done and all that, because some people are really damn crazy. Who knows what the laws are going to be in the future, considering all this other misanthropic sort of behavior that's happening around the place. Who knows? It is worrying. But anyway, back to this. In established drugs or treatments that can be devised that interfere with it to combat obesity, as I said, we can intervene using this circuitry, whether or not you have the risk variant, he says. So it's something that I wouldn't advise as an approach to health, but this is what they actually say. Now, this is the actual study. Okay, so this is the key variant that has shown the strongest causal inference according to these researchers. In my case, I've got a CT allele, which basically puts me in this category, which doesn't surprise me. I've got a 2.5 odds ratio. So the risk is a 1.3 fold. Obviously, if you got that one, it's a 1.7 fold increase in obesity. So in increase of fat mass. So basically these people probably can tolerate slightly over 50. These people should be under 50, and these people should be definitely under 25. So that's the sort of, when we're talking about carbohydrates here, as a general rule of thumb. So when we look at the populations, so the TT is the sort of what we call the normal. And if we look at the populations, Kenyans are about 75, you know, this other group in Kenya is about nearly 100%, you know. So Chinese are 74, Japanese 65, Nigerians 88, West Africa. This is from the South, people with African ancestry. So the southwest of the US, so 79, which is similar to some of the other African populations. Chinese in the US, similar to Chinese in China, just slightly less. Different areas. Indians about 50 odd, still better than the Europeans. When you look at the Europeans, only about 30%, less than 30% are in the sort of norm. Everybody else is, you know, like Southern Europe. I mean, the Italians probably represent the Southern Europeans and the Mediterraneans. You know, looking at 44% and about, you know, 27%, slightly less in Northern, but still quite high compared to at the same level that I am. You know, it sort of explains why, you know, we see most white European descent people, you know, morbidly obese and obese, you know, all that far more than we see Asians or we see people from Africa and places like that. Probably some of those Africans that have got probably some genes that come from European descent, mixed to some extent, possibly explains why some of them are quite overweight. So it's all sorts of different elements, but we do notice certain groups in particular. The Nigerians basically have none in the high risk, and the same thing with this Kenyan group here and the Maasai. So they're pretty much safe, all these groups. Now, why would this be the case? Why would basically most of the rest of the world be more dominant in this, and why the European populations more dominant in these? Well, let me just go and give you a bit of a background explanation for that. If you take a look at China basically, beyond a couple of civil wars here or there, it's been pretty much a unified entity for a very long time, which basically means that for a very long time, there wasn't consistent warfare. You know, they had Mongol hordes a bit, that's about it. And even when they were occasionally conquered by them, you know, they pretty much just took over the empire and then they were pushed out at some point. Southeast Asia, you know, it's another area with a lot of food. India, massive river system, supported by a lot of silting and all that, you know, so provides a lot of calories and all that. And in parts of Africa, you've got big waterways, plus you've got basically, you know, good hunting grounds and all that for a lot of the tribal people. So you don't have this sort of scarcity. What do you have in Europe? You have small kingdoms that are in constant, also city-states or whatever, that are in constant conflict with each other for thousands of years. What does that mean? It means that basically you've got long periods of time of massive deprivation. So your cells have been, or your genetics, these genetics have been altered for one bloody reason: to seek out every single fucking calorie. So when you get slightly excess calories, it stores it. If you're in an environment of plenty, you don't need to do that. Your you'll basically go, yeah, a bit more this time. Let's just basically, uncouple and get rid of it. And when you've got those, you've got the TT alleles, that's what you're going to do. So it's much harder. And usually those populations would have basically, because of their physical activity and other things like that, they wouldn't basically generally engage the randle cycle anyway. Today they do to some extent, but even then they become more diabetic than obese, if you take a look at most of these Asian populations. So our white adipose tissue behaves a lot different because of this sort of period of time in our history that, well, for thousands of years that we've been at each other's throats. It's the reason why Europeans are very good in terms of military technology to this day, or European descent populations, and we're able to conquer many parts of the world. It's when you basically are killing each other left, right, and centre, you do innovate in military technology, but at the same time, you end up with genetics like this. So that's the downside. So there's always both an upside and a downside, and that's the downside. Okay, we've got a couple of other snips as well, play a bit of a role, and this one, oh, well, actually, that's that one there. That one they do suggest may play a sort of a minor role. I'm again fucking middle. Thank you to my European ancestry. So AA is normal. As you can see, most of these populations are AA again. Again, the Europeans are very low and tend to have the worst. This one, this variant, 25%, this variant, 21%. And that's another obesity-related trait. So again, the Europeans, both the Northern Europeans and the Southern Europeans, tend to be the worst in that regard. This other group is Indians in the US. So Gujarati Indians. So yes, anyway. And so pretty much, again, we can see the influence of past history has an effect on our genetics. And so this one is also related to obesity. Anyway, now let's look at the other ones. This one is also, so those effects on the BMI. And again, as you can see, the normal is TT. Again, here we've got similarities with these populations. So we do have some similarities with a couple of these populations. Even with the Maasai. So this is an interesting one. So it's a trait, and this is probably one that's been around for a very long time. And the only reason for the Japanese and all these people, if you take a look at the populations that are not affected, are populations that have consumed more carbohydrates. So this is probably a more ancestral one, I've always said, as an obesogenic one, rather than, something that's actually been more recent. And it would be understandable why it actually was reduced in the Chinese population, all that, consuming more carbohydrates. And I'm somewhere in the middle for that as well, which puts me in the 1.3. I'm middle of the road in terms of risk on, I think, on all of these from memory. This is another one, another gene. And in the middle again on that one as well. So that's one that is really, this one is a really biggie. As you can see, these people have got much lower risk. So it's not only, you know, they're actually got a 1.5 reduction in risk, not, you know, so this is actually an increase. So if you think here's they're going that way and these other ones are going the other way. So, and again, see the TTs, which is again, Chinese, all the Asians, again, the other groups, and that is also another traditional one because it's basically found in Africa and Europe. And again, that's because the Asians had high carbohydrate diets for a long period of time, in particular the Chinese, the Japanese. We know they've had those sort of periods. So I've already covered that. But the key one for deprivation, because these ones are all related to type 2 diabetes and stuff like that, and the obesity risk, but that's the primary one. And that primary one is because of those historical reasons that I explained earlier. Anyway, now, this is the IRX3. So I don't have that genotyped, and I don't have the others because I've already checked them. Just wanted to demonstrate that. So the genetic test that I did, it's not in it. Unfortunately for me, if you done a more comprehensive one, you'll probably find those in there. Oops, let's go back here. And the other ones are these three here, which is I'm not going to look at them. So I'll just bring up one. So it's pathogenic Hammermanni syndrome. So it also relates to this sort of syndrome as well. So just letting you know. But at the end of the day, it's really this one here that's the important one. Do you have this? Then you can activate the other ones to burn off adipose tissue or to store more. So this is the key one from all the research in that regard. These are other ones that I've come across which are related to this and have a risk factor as well. So this is just for additional stuff that people may be interested in that regard. So I'm somewhere in the middle again, middle of the road. And in some populations, so there's a risk in some populations. It doesn't necessarily mean you are going to be at high risk or not. This SNP is in a linkage block in the FTO with both that and the other one for the association of this block with earlier onset obesity, since it has shown a strong association between the two. So if you've got both, which is this one here, I'm in the middle of that as well. you very much, my dear parents. So, and again, if we look here, CC, again, Chinese, Japanese, Chinese, so Mexicans. So pretty much again, the worst ones. Nigerians, African descent, Kenyans, the Maasai, and Southern Europeans and Northern Europeans. So this is more an ancestral one. So populations that have never had a high carbohydrate diet. Now in the modern world they do. So that's how you work out the differences between the two. There are a couple of other sort of minor associational stuff and all that in different populations, sort of Japanese study and other things like that, other people may want to look at for additional information. That's not the focus. The big one, remember, is this one. So the single nucleotide polymorphism is that one, and those that are the alleles that you may have or not to look at. Let me just start the sharing. So this is sort of an insight into sort of the genetics. And so by looking at those genetics, you can make some adjustments to the way you do your low carb diet, whether you're doing a keto, a standard keto, a low carb carnivore keto, or a low carb carnivore approach with some dairy and stuff like that. How you mix and match and how you approach it, having a look at your genetics, can give you insights to say, well, maybe I should go a bit lower on the carb side, or I can tolerate a bit more. Usually the giveaway is you notice the effects. Looking at the genetics will basically bring to your attention the potential implicators on how well you can lose weight and all that. So as I usually laugh and joke with my friends, I say I can look at a carb and put on a couple of kilos, and if you're in the worst category, you probably can put a couple of stones. But the reality is that some of us have a better capacity with carbohydrates. Some of us, like me, not the worst, but still not the best either. Somewhere in between those two groups in that regard. So, it's really important that certain people are aware of these sort of things, and it may explain why they get plateaus, why they struggle, and why they may have to go even lower than usual. And it may be not something that people want to hear because they've already, made changes to their lifestyle and don't want to make any further. But at least, you're informed, you know what the situation is, what some of the factors may be there, and then what steps you take is up to you, your body, not mine. So this is not meant for in terms of medical advice or anything like that. It's just a general outline of these genes that are playing a role. How you modify your diet is up to you. This is the insight you can compare. If you've done genetic tests, you can look, and then that will probably give you a bit of an insight what may be, affecting, the way things are happening in terms of with your weight loss and stuff like that. So I hope this was a bit informative, give you a bit of insight on the world of genes and how they can have an effect, and what's potential insights you may have in terms of modifying your own lifestyle and dietary practices. Anyway, see yous.